Hello community, so great to see you. Today we have some complete new ideas, unbelievable. And we have answers regarding mathematical reasoning, code reasoning, and how to best train with supervised fine-tuning and reinforcement learning. And let's start. You know, there was one paper from the video of yesterday that I told you, let's have a look at this. And I said, hey, the mathematical leaderboards, now they improve week by week. And now it is worth asking here, do those performance gain that we see here on the theoretical leaderboards really reflect the broader problem-solving ability of those models, or is it just a narrow overfitting for mathematics? Or if you can say, does learning the mathematical reasoning really improve here also the general reasoning functionality of a large language model? Now, easy. Let's have a look. Let's take 20 LLMs. Let's have the Math Reason benchmark here, famous one. Then go with other reasoning benchmark for the same. And then we have some non-reasoning benchmark here. And let's just compare the data. Now, we do have a brilliant new idea. I mean, the authors had a brilliant new idea. We define here a transferability index. And this index is simple, tells you how much better the fine-tuned model is on that specific group of tasks. The index here measures how much of the gain and now the mathematical reasoning that we trained it for now successfully transferred to other domains. Maybe in code, maybe in question and answer, maybe in scientific, whatever. And we have here for other and non, so other reasoning benchmarks and non-reasoning benchmarks. And if we have a positive TI, this means that the model successfully transferred its reasoning gains to a new domain. Great. A negative TI, on the other hand, means, oh, we have now fine-tuned something on mathematics, but catastrophic forgetting happened here on the LLM. Therefore, the LLM forgot other knowledge. We did not really override the knowledge, but it is not anywhere available anymore. Here you have it. Here for the base model, beautiful, then the 7B versus the 32B, and Qinyuan versus the Llama. We operate here, remember, Qinyuan 2.57B and a Llama 3.18B. So you see here, TI other and TI non, positive, negative, and you immediately get a feeling for the model. Unbelievable. Just have a look here at Stanford 1.17B. And the Stanford 1.132B. For other, it switches here from a negative into a positive. So every model is absolutely specific in this benchmark. Now the shocking result the authors found is, we find a clear pattern. Those models that were here trained with reinforcement learning showed positive TIs across the board. Models trained with supervised fine-tuning often showed a horrific drop in the performance, a negative TI performance indicator. Those models with supervised fine-tuning trained became math experts, but at the cost of their general knowledge. So they become here, if you want, some experts only. If you want to read more or see more here about Stanford University, the S1 model, this is the video for you. And now the authors decided, you know what, we have to do a controlled experiment. We want to understand where does this originate from. So the author said, okay, let's take a Q13 14 billion free trainable parameter model, the base model, and let's ensure that if we do now the supervised fine-tuning and the reinforcement learning, they are trained now on the exact same data, information, knowledge, and let's analyze their capabilities. So they created here 47,000 high-quality mathematical problems. And then they ask here, a teacher model, this is a Q13 32B, so much bigger than the 14B, to write here, if you want, the reasoning traces. Great. And then this is it. Because now you can create two data sets that is based on the same data. No? For the supervised fine-tuning, you know, this is kind of, if you want, imitation learning. So you have given a problem and you provide to the AI a perfect step-by-step solution. And let's say this is here by your bigger LLM by Q13 32B. Or you have reinforcement learning. Then you wanted the AI finds here the solution itself. So just provide here the input, the problem, and the final answer, but not a step-by-step solution, because they work differently. So you see, perfect. Now we have the data. So just we take two Q1 14b and let's train them. As I told you, supervised fine-tuning, if you want, they call this the Uni-Reason supervised fine-tuning. Beautiful. Now we have a new model. Supervised fine-tuned here, and this is a kind of a process mimicry that's happening. No? You minimize here in the simplest case here the cross-entropy loss between its own output and the teacher's perfect chain of thought solution that is given. If you can see in Q13, yes, you can see really the reasoning traces. You cannot see this, for example, with the latest Google models. So this was easy. And for the reinforcement learning, you have here a GRPO. This is, if you want, here the outcome seeker, and the AI has to find its own path forward. Let's have a look. This is another performance benchmark. If we have now the supervised fine-tuning model here and then the reinforcement learning here. For mathematical reasoning, if we do supervised fine-tuning, we get a performance jump 22%. Great. RL, 26% over the base model. Other reasoning, plus 15%. But look at this, with reinforcement learning, we get close to 30% improvement over the base model. And for the non-reasoning, as I showed you, now from those benchmarks, we have, with the supervised fine-tuning, we have a loss. The model forgot its knowledge, override it, deleted it, whatever happened. Now the model is not able anymore to do non-reasoning tasks, since it was supervised fine-tuned on mathematical reasoning. But the situation is different here for reinforcement learning, because they could also improve also only 7.5% over the base model. Now this is interesting. So if you go now and say, I have a base model, I train it now with supervised fine-tuning on mathematics, then you will have a good mathematics. If you do with RL, even a little bit better. However, if you want to do some other reasoning with the same model, you see it is definitely recommended to go with reinforcement learning and not with supervised fine-tuning, because this causes catastrophic forgetting. Great. So again, they call this with the supervised fine-tuning the process supervision, and reinforcement learning the outcome supervision. Forget those terms. The result is clear, improved on math here, other reasoning and non-reasoning task, reinforcement learning. Great. So this experiment proved that here the training paradigm that we use, either supervised fine-tuning or reinforcement learning, is the key driving factor for the transferability of knowledge. Interesting. But why is supervised fine-tuning really damaging the model, the capabilities of the model? And the authors went further and said, you know what, we can have a deep dive to try to understand inside here the Q13. So they say what we do, we just have a look at the model hidden state at the activations in detail, and what we do a PCA analysis, the principal component analysis, and we do here PC1 and PC2, just to see here how is here the configuration. And in addition, if the model understanding is preserved, and you know we have an autoregressive model with next token prediction, this shouldn't change a lot of. So the next token prediction for mathematics and the next token prediction for non-reasoning should be rather similar. See Kullback-Leibler divergent terms. So they did this. Easy. Computed here the principal component, PC1, PC2 from the base model, and then they projected the hidden state from both the base model and the fine-tuned model onto the same components. They calculated the center point, the centroid of the projected activations, and then they could see here a difference in the Euclidean distance between the centroid of the base model and the centroid of the fine-tuned model, and they call this parameter the PCA shift. Simple. You know what? They do the same here with the token rank. They say, okay, Kullback-Leibler divergence measures the difference between the next token probability distribution of the base model and the probability distribution of the fine-tuned model. A higher Kullback-Leibler divergence means a greater shift. So we define now the token rank shift. Generally, the token with the fine-tuned model will likely have a rank 1, But what was the rank of the same token in the base model prediction at that same point? If it was 5,000, you see, oh wow, there was some significant shift, a rank shift here, token specific. So let's have a look at what are the results. The PCA shift for the reinforcement learning tuned model was rather small across all task types. This is good, so say, okay, beautiful. But look what happened with supervised fine-tuning. They showed here a massive PCA shift, especially here for non-reasoning inputs. We've seen this already. You remember the drop here in, I think, -24, -26% happening here in the performance data. So supervised fine-tuning was not adding new knowledge. It was kind of violently distorting here the model's entire existing knowledge structure. It mixed up the knowledge and it deleted and overwritten some knowledge. Now, let's have a look here at the token drift. We see here again that reinforcement learning is here really precise like a surgeon, no? Selectively changes here the ranks of only a few key tokens relevant to the task. But supervised fine-tuning, absolutely contrary. Supervised fine-tuning is a sledgehammer. It causes massive indiscriminate shift here in the token rank. If you want to see this here for reinforcement learning, look, if you have this word cloud, these are the very few tokens that were shifted. But if you compare this to supervised fine-tuning, you see, oh wow, supervised fine-tuning just went in and moved everything around. An indication that reinforcement learning is a much more delicate but much more powerful instrument for tuning. So the authors tell us, hey, rather be skeptical for supervised fine-tuning if you want to do the specialization. When you fine-tune a model on a narrow data set using supervised fine-tuning, and it's independent if you're in medical, legal, or you have some company documents, you risk harming its general abilities of this model. So always evaluate for catastrophic forgetting here on a broad set of benchmarks before you really implement this finally. Now with outcome-based reinforcement learning here, it allows the model to preserve its internal knowledge structure to a much higher level while still learning new skills. So this is much more robust path of creating models that can specialize and generalize at the same time. If you want to see here the numerical data here for all the different benchmarks here, this is here the average token rank shift of supervised fine-tuning and reinforcement learning models. You see, RL is here much better. And of course, we have here the Cooper-Claver divergence analysis again for supervised fine-tuning and reinforcement learning. And again, you see reinforcement learning is better. And the authors have thoughts like, the future could be hybrid, You will have an effective training with some careful use of reinforcement learning, perhaps combined with a very targeted and a minimal set of supervised fine-tuning to build one of the incredible general knowledge here of the foundation models without destroying the inherent parametric knowledge of our foundation models with the post-training of RL or supervised fine-tuning. If you want to see this, because honestly, this is what we do for years. 2 years ago, I showed you here, if we coded here supervised fine-tuning with DPO, and in this video, I showed you here reinforcement learning where you went feedback with DPO on a path, LoRa, 4-bit, everything. We coded this together. And of course, we also went from DPO to TPO to test time preference optimization. Great. But knowing this or having here a confirmation of our old knowledge, now the second paper really changes everything. They have here, it was submitted 2 weeks ago, but it took some time to be officially released. We have here Fudan University and Shanghai Artificial Intelligence Laboratory, Implicit Reward as a Bridge, a unified view of supervised fine-tuning and DPO connections. Now, this is an absolute fascinating paper that says now, you know what? There's a connection. Because up until now, and I just showed you this, supervised fine-tuning was kind of a little bit of a warm-up. DPO is where the real alignment happens. And now they tell us, hey, wait a minute. We looked at it from a very particular mathematical perspective and we found supervised fine-tuning and DPO are not different processes. They are both doing here the exact same thing, optimizing an implicit reward function. Supervised fine-tuning is simply a very special and surprisingly flawed version of DPO. When I read this, I said, this is not possible. How can supervised fine-tuning? Look at the code, look at the implementation. It's completely different to DPO. How can it be a special version of DPO? Well, they show us here a beautiful, elegant mathematical framework for understanding here both major post-training methods, SFT and RL. So they say it's like finding a unified field theory for LLM alignment. Absolutely new. And you know what is the beauty here? It explains here the sledgehammer effect from the first paper that I showed you. Now we have a mathematical explanation why it is happening. In the first paper, we just found here with the experiment that it is happening, but we could not understand why. And you know what? It's easy. It is the absence of the Kullback-Leibler term here explaining why supervised fine-tuning can be so destructive to a model existing knowledge. It allows here the model in the training to drift too far from its learned, robust base state. It is just drifting completely away in a non-controlled fashion. And we do not have here the Kullback-Leibler term, comparing here probability distribution. It is simply missing. And the authors put here supervised fine-tuning under the same mathematical microscope as DPO. And they say, you know what, we developed now a mathematical theory that we can show you that the standard supervised fine-tuning loss function is actually missing here a crucial component. And this is the Kullback-Leibler divergence term that we have in reinforcement learning. Absolutely fascinating. And you know what? They even went a step further and they said, we know how to fix it because now we know what is the cause of supervised fine-tuning failing. They provide three kind of fixes, and the simplest is just lower the learning rate of supervised fine-tuning. Of course, if you reduce the learning rate, you stay closer to the original distribution. You are not drifting away somewhere else here, but you stay to the parametric knowledge of the base model. You don't deviate too much, so therefore, what a simple solution. And they did the test and said, yeah, it yields significant performance gains. Let's continue. Do you remember imitation learning? I had some videos on this about 2 years ago. And we had a concept in imitation learning. It was called distribution matching. And the goal was simple, to make the model's behavior distribution match the expert behavior distribution. And the objective was to minimize here the distance between those probability distribution of the expert and the student, while also keeping the model from straying too far from its original pre-trained state. And you remember in this objective function that we defined, there was a divergence term. And here we have again our F-divergent. Now, if you're not really familiar with this, never mind. This is here the general objective here. Very simple formula, and you immediately can identify this. We have here our F-divergent term with here the expert state action distribution. And of course, here we have the Kullback-Leibler divergence. And we will split this into the entropy term and the cross entropy term. So these are our good old friends here from the formulas. Now, remember, the F-divergent is kind of a toolbox of rulers. It is a generalization to measure here the distance between two probability distributions. So we are deep in statistical physics or statistical mathematics, no? And remember, we had a lot of possibilities to do this. Now, this function f here, the authors now continue to show that we have different choices. Whatever we define as f will now really change here the training objective. And we will find training objective that we already know. So f here is the dominant or the super function, whatever you like to call it. It is a special kind of function, convex, beautiful, that takes here this ratio and decides how to penalize here for the difference between these two probability distribution, let's say from the teacher and the student. And the simplest ruler that we have, the simplest distance, is a total variation distance. So the authors prove that the standard here, supervised fine-tuning, this is the ruler that works with supervised fine-tuning. And this is a simple function here. Here you have it. And what it does? Easy. It measures here the largest possible difference in this probability distribution that the two distributions can assign to the same event. Simple, straightforward measurement of divergence of probability distributions. Great. But you know that there is a flaw, because when the authors plugged in this specific ruler function into the unified framework that we're going to have a look at in 3 to 5 minutes time, they derived it a special conjugate function, and in calculating further, they found that this crucial Kullback-Leibler divergence term completely disappears from the gradient during the optimization process. This is not what we want, because suddenly this element here has no gravitational effect. It keeps it close to the original probability distribution of the parametric knowledge here of the teacher model. It just drifts off again. Nothing is holding it back. So choosing here the total variation ruler is mathematical equivalent to performing here the standard supervised fine-tuning in this new mathematical model. But the negative effect is that it cuts here the leash to the base model, and now the student model allows here for dangerous knowledge drifts happening in all dimensions. Now the author said, that's easy. We can fix this problem with supervised fine-tuning here. We just use here a more intelligent divergence, the person chi-square divergence. So this is an easy function, as you can see here. What it does, it heavily penalizes points where the probability ratio is very large. So it is more sensitive to those spikes in the model probability distribution compared here to the experts. Great. So when the authors plug in this ruler, this function, into their new mathematical framework, the mathematic works out differently. The resulting training target becomes much more complex, but it preserves the Kullback-Leibler-like constraints. And this is what we want. We want to have a kind of a constraint to the parametric knowledge distribution here in the policy. So it doesn't let the leash go. The final loss term still remembers here the reference model and keeps the new policy from straying too far. Of course, they did this not only for the total variation or for Pearson chi-square. They had the square Hellinger, and there's a lot of other. If you want to have a look at this, you find this here all in the paper. They had then a calculation of the training target, and great. Now let's have a look here at the downstream results for the different training targets and their post-DPO checkpoints. We have here Llama 3 base 8 billion model and a Mistral base 7B model, and 3 identical benchmark for both of our two models. At first you see here supervised fine-tuning, and then with DPO, those are the performance in the traditional supervised fine-tuning. And then we go with Pearson, supervised fine-tuning and DPO. And then we go here with Hellinger, supervised fine-tuning and DPO. And you see their performance increase here, but it's not really massive, I would call them. So I think the beauty of the paper is absolutely in developing a new mathematical model, combining now supervised fine-tuning and reinforcement learning. And the way they do this, you have here, for example, Theorem 3. So they have a lot of ideas that they write in mathematics, and then, for example, this simple expression here, if you want to have a look at this, they give you a mathematical proof and they say under certain conditions, we think we can substitute these terms or have here some other approximation working. Now I have to tell you, just reading this paper, I cannot tell you if this is here a correct way to do it or not. So I need to go my next weekend, really take a time off, sit down in the garden somewhere, just a piece of paper and this publication. And I have to go through all the calculation myself because I want to understand it. I want to understand the restriction that they imposed, but I just want to get a feeling for this. So today, I can only tell you here in this video, this is what they published. But if you ask me here, could you really understand here to the ultimate depth here if this mathematical theorem is here really the new model? I have to tell you, you have to wait till next weekend. I can't tell you at the moment, but in some days, of course. Yeah, supervised fine-tuning is a special case. I already told you that you can do some substitutions, yeah. But let's come back here to the main topic. I wanted you to understand the main idea, the way I understand it. So by using now here this F-Divergence framework, the paper kind of demonstrates that supervised fine-tuning and DPO are not fundamentally different. They are just different rulers here from the same toolbox, measuring here the same distance, but with critically different properties. Plus, the authors tell us, the ruler that we used for supervised fine-tuning has a major defect. The Kullback-Leibler divergence disappears in the gradient optimization. So, knowing this now, you can find solution. And they also tell us, you know what? The total variance distance, again, if you plug it in and use this, yes, these are all the mathematical formulations that we are familiar with, no? And they tell us, hey, this equation here is exactly the bridge, no? It shows that here supervised fine-tuning is fundamentally doing the same thing as DPO, optimizing an implicit reward. And up until this moment I said, so they tell me that they develop a mathematical framework. And in this framework, after a lot of complex mathematical calculations, a lot of, let's say, constructs that they include and a lot of assumptions that they include, they come to the conclusion it is more or less the same, just with a different F-divergent term, but the model is the same. You have kind of a unified field theory for this. And if you want the ideas in both systems, optimize an implicit reward function for the system during the learning process. And I said how you can how you can implement this on a pure mathematical level. And then I read it later in the study. You see, they use inverse reinforcement learning. Now, in my understanding, this idea that they then convert to mathematics, this is the main bridge between supervised fine-tuning and reinforcement learning. Because what is the core idea of inverse reinforcement learning? If we assume the expert, we are imitating our teachers. They are rational and they are effective and they are not just taking random actions. So they must be acting as if they're trying to maximize some hidden internal reward function. So instead of just blindly copying their actions like in imitation learning, the idea is now, can we first try to figure out what their hidden reward function is of the teacher LLM, and then just learn to maximize this reward, because then automatically we will arrive at the same, if you want, internal reward function that perform here an imitation learning process. So you see, at this moment, I said, okay, now I understand what they did. They had an idea that this is the bridge between supervised fine-tuning and RL. They said, it is not it's just supervised fine-tuning is imitation learning. No, they said exactly, we need this additional sort that those teacher models also have the same inherent logical, causal, reasoning core functionality to maximize an internal reward function. And now with this idea in the theory, I can build a mathematical, if you want, environment. Yes, but this is an assumption that we have from the idea. And this does not deduct from a mathematical field theory. Yes, it kind of deducts, but at first you have to have this idea that you build a mathematical field theory in a way that it then comes out. So, okay, you see, I'm a little bit confused because I need a weekend for this paper. Yeah, by the way, if you read the paper and you see this in mathematics, and I know there are people that are gifted in mathematics, and either you say, yes, I can confirm, or no, I see a problem, please leave a comment for this video. So what the authors did is simply to reframe here the imitation learning, and this is more or less supervised fine-tuning, no? As an inverse reinforcement learning problem. And now everything is clear, no? So they said, let's not treat supervised fine-tuning as just some dumb mimicry, but let's assume the expert demonstrated in our supervised fine-tuning data set. Those data sets are the result of an agent acting optimally according to some implicit reward. And if we make that assumption, then the problem of copying the expert with imitation learning with supervised fine-tuning, then it becomes mathematical equivalent if we build a theory that respects this idea to finding and maximizing the implicit reward for both systems. So inverse reinforcement learning, which then becomes suddenly a normal reinforcement learning problem. Okay, now we are good again. So you see, now I understand that both supervised finding and DPO are now playing the same game. Because we assume that both play the same game. And then we just need to build the mathematics in the specific way, no? So they are both trying to optimize here an implicit reward function. Great, this is now the new paradigm. But this, if they do the same, analyze them here in the same mathematical tools with F-Divergence. And when we do, we find here that they operate in the same mathematical space. So let's have a look at the space. Now the authors tell us, hey, if supervised finding and DPO are both moving around in the same optimal policy reward subspace, they just take different paths from the beginning to the end. Absolutely fascinating. So what we have, what is this space? The X dimension here are the space of all possible policy models. The Y dimension represent here the space of all possible reward functions. So each possible, theoretically possible policy will have its own expected return function, forming here a curve in the policy return plane. Okay, let's look at this for supervised fine-tuning. So we are moving along a mean gradient into optimal policy subspace. Okay, I can go with this. And then you see A, whereas A, the expert policy, this is the supervised fine-tuning target point that we want to reach. And B is, I suppose, here is the search direction along an optimal path from B to A. Great. What is I? I is here the supervised fine-tuning starting point on the optimal path. Well, congratulations. And then we have here blue vector to H1. A blue vector is the average direction from the data point to the expert. Well, okay. H1 is a training data point along the optimal path. Okay, yes, what else? What are the little red stars? They are the optimal points for each reward function. Oh, okay. You see a beautiful hyperplane. Okay. I mean, yes, of course. What else? But let's look here at the DPO now in the same space. Moving along here the chosen or rejected direction, the optimal policy subspace. So where are we? Well, what is E? E is here the reject. Okay, we have rejected sample. Yes, of course, we are DPO. Then we have C is the current optimal policy. Great. Then we have a green dot. The green dot is the current optimal policy. Okay. And then we have the red star. This is the optimal policy, the optimal points for each reward function. And then what we have in lila, we have here a vector. Where is it? This is the DPO direction. Well, yes, of course. What else? I mean, okay. Good, yeah, this is beautiful. But you see, the idea, you just have to have an idea. And I love this, no? So the second paper now, and this is why I've chosen this paper here for today, provides now a deep and a kind of satisfying theoretical mathematical foundation for the empirical observation that we noticed in the first paper. I don't think that the authors know from each other. But me, looking at this days later, I can see that those papers relate. No? So they reshape here my understanding of the LLM post-training process involving here supervised fine-tuning and reinforcement learning. And we now know that supervised fine-tuning is not just here a simple warm-up like we thought. No? It is a flawed, but a kind of a repairable form of an internal reward learning mathematical operation under the same fundamental principle as DPO. This is amazing. This is a kind of a unification of this post-training methodology. So, summary. Supervised fine-tuning is just imitation learning with a very specific F-divergence. It is the total variation. So I think this is here the second paper's most direct and most amazing claim if you accept the mathematical framework. But let's assume everything is good, everything is perfect, they checked everything before they published. Great. So by framing supervised fine-tuning within the general mathematical framework here of imitation learning, they prove now, see yourself, that the standard supervised fine-tuning objective, the maximum likelihood estimation, is not some unique process, but it is the exact mathematical solution of choosing here the F-divergence as a total variation as your ruler to measure here the distance between your model and the expert data. And this is the same process like in DPO. But careful, DPO is not just imitation learning with an F-divergence of Kullback-Leiber. No, and you know why? Because the DPO objective is constructed differently. It works on preference pairs, you know? You have a chosen response and a rejected response. So you do not have this single teacher LLM, but you have a pair, a dual pair. So therefore, the DPO entire objective is built around this very Kullback-Leiber term that supervised fine-tuning accidentally eliminates here. Now you remember that the loss function for DPO had a very simple structure in a simplification. Yeah, this is not the most complex form, but you see the Kullback-Leiber F-divergence is here not just an added term. You see it here, and these are kind of the fundamental building blocks here of the entire loss function for the winning and losing responses. No? So this is absolutely focused here on Kullback-Leiber, and this is the reason why DPO works so beautifully. And like supervised fine-tuning, the DPO objective is, of course, is equivalent to optimizing an implicit reward model. And this is here the shared unifying principle connecting supervised fine-tuning and DPO. If you see it from this perspective now, after having read the paper, after seeing now in the formulas here the connection, you might think, hey, they might be on to something. Now, again, summary. So it really depends here on the choice of our ruler for the differences here and the probability distribution for the F-divergence. If we choose the total variation, we will arrive at the supervised fine-tuning. If we choose for the F-divergent Kullback-Leiber, we will arrive at a known DPO methodology. And now, in the first part, in the first half of this video I showed you, supervised fine-tuning is not ideal. Reinforcement learning is so much better. But now we can correct supervised fine-tuning, understanding what caused its malfunctioning of catastrophic forgetting. My goodness, we have an explanation why it happens. So we can now compensate for this mistake. So let's go with a person chi-square, F-divergence, and you get an improved supervised fine-tuning. And the authors tell us, hey, we did the calculations, have a look yourself in the paper. This creates now a new SFT loss function that finally preserves the Kullback-Leiber-like constraint, preventing thereby the drift of the knowledge away from the, if you want, parametric base model. Great. This is what I wanted. Okay. So I think the beauty, if you're one of these second paper, is really, we don't need to throw supervised fine-tuning away. We just have to understand what it really is. And I think the second paper, the second half of this video showed you, if you look at it from a particular perspective, and quite heavy mathematical framework, we understand why the failure happens and we can correct it. We just need to pick a better ruler, a better F-Divergence to make supervised fine-tuning behave more like a DPO. A well-behaved, least constrained learning process that respects here the model foundational knowledge distribution. And the authors tell us simple learning rate reduction here to make here supervised fine-tuning better yields significant performance improvement, and as they say in their internal experiment, up to 25% relative gain. I have to believe this? Okay, but absolutely fascinating. So here we go. We started to examine reasoning in mathematics and non-mathematics, in code reasoning, in non-reasoning tasks, and we understood it all depends on the training process, how we train our LLM. And then we found out that what we saw, the two building blocks, supervised fine-tuning and reinforcement learning, are more or less just two sides of the same coin. And this coin is a new mathematical framework to understand that both models do the same. They optimize an internal reward function given a specific assumption that works here on both models, supervised fine-tuning and reinforcement learning. I hope you enjoyed it. I hope you had a little bit of fun. I have a real beautiful weekend in front of me in some days. I'm really looking forward to trying to understand the mathematical framework. And if you are interested in this kind of videos, I know it's a little bit crazy, but hey, why not subscribe? And I see you in the next one.